Okay, in this video we are going to look at some of the trickier questions from the homework for topic 3 and try and show you some modelling examples in case the mark scheme hasn't been enough to give you a hand. Okay, so in this question we're just focusing on part C, this first question, question 4, and it's an analysis question, so I think we should start with some tips. When you're analysing a graph, the first thing to do is make sure you mention both variables. So here the variables are the year and the percentage of total energy that came from renewable sources. And I haven't even read the question, but I know I'm going to talk about those two in my answer. And there's 4 marks available here. I'm going to need to link the relationship, the pattern in the results in this question between the time and the percentage of the total energy that's come from renewable sources. Okay, so that's what I'm ready to do as soon as I see it's a graph question, to be honest with you. So we're being told about between 2 times, and we're being told about countries using renewable and non-renewable energy, because if the percentage total energy that comes from renewable sources is shown on this graph, that means the rest of the 100% is the non-renewable sources that were used. So figure 6 is showing us that percentage of total energy, and therefore I can see that there is a trend, and I've got to explain the trend, not just state it. I've got to explain it, and that's why this is worth 4 marks. This isn't just say what the graph shows, it's say what the graph shows and then use your science knowledge or physics knowledge to explain it. So we've got to look at the trend, and we've got to look at the benefit to people and the benefit to the environment. Oh, benefits hasn't got 2 E's in it. There we go, sneak that in. So first thing I would do, number 1, first mark, I would talk about that relationship, that trend. As the time is going on, we can see there is an increase in the percentage of total energy that comes from renewable sources. So I would start with the idea that the trend here is that as time passes, more and more energy comes from renewable sources. The percentage of total energy that is renewable increases over time. Then I would come to the link to what that means about non-renewables. Second thing I would do, so trend for the first one. Second, link to the question. I would point out here that means if we're using more renewable sources, that we've reduced our use of non-renewable fuels. So we're using less of the non-renewable things like coal, oil, gas, the fossil fuels, and the nuclear fuels like uranium. That's probably got me 2 out of 4 marks. So the third thing I need to do, the third thing that I need to do is I need to think about the benefits. 1 mark for people, 1 mark for environment. So the benefit for people could be that renewable sources typically have no fuel costs, and so the energy could be cheaper, which would benefit people. And then for that 4th mark, so I did people for that one. For the 4th mark I'm going to do environment. And for the environment, using renewable sources will mean that we don't have to use as many non-renewable sources, so less coal, oil and gas being burnt, being combusted, which means less production of the greenhouse gases like carbon dioxide. And I would be specific and mention a greenhouse gas. So I've mentioned carbon dioxide. So less pollution in the form of carbon dioxide, which is a benefit to the environment. I think that should get us the 4 marks. Demolition ball. And we're told right in the beginning of this question, a useful piece of information, that the mass is 400 kilograms. And kilograms is the standard unit. We're being told that this ball swings from A to B, so you've got gravitational potential energy changing into kinetic energy in this swing, and it's moving through a height. We are therefore told the change of height here is 1.5 metres, and metres is the standard unit. It's all looking good. We're being asked to calculate the change in gravitational potential energy. So we need to recall the equation. Gravitational potential energy is all to do with mass times by the gravitational field strength times the height. We know the mass, we know the height, and down here we're told that we need to take G as 10, so we know that too. So substituting our values in, they're all in their standard units. We have got 400 times by 10 times by 1.5. When we times those three numbers together, obviously using a calculator, don't do that one in my head, that will be 6,000 joules. And as we're not actually told here what unit they want that in, you could also say that is 6 kilojoules. One of the reasons that the mark scheme may have thrown you a little bit here is because even though in the exam question here it told you to use the gravitational field strength G as 10 newtons per kilogram, for some reason in the mark scheme here it has it as 9.8, which is actually a more accurate value, but that is not what the question told you to do. Therefore it is 400 times 10 times 1.5, which gave us the 6,000 joules, which is the correct answer. This was a put together mock paper that was made, I should imagine, with quite a small time frame when this exam was new, and this has never been sat as a real exam, so it hasn't been through the normal review processes that it would go through, and therefore the odd error does creep in. So there is also part 2 of this question, where we're being told that the heavy ball comes to rest after smashing into the wall. So we've got the wall, got the ball has swung and hit the wall. In doing this, we're told the temperature of the ball, the wall and the surroundings all get a little bit warmer. So we're definitely going to get to use our favourite phrase of topic 3 in a moment. Right, the energy transfer is happening here. Gravitational potential energy of the ball is being transferred into kinetic energy of the ball. The ball hits the wall. It was moving. It then causes the wall to move. So there is kinetic energy in the wall. And this is all useful. But because of air resistance, because of friction, because of the collision that's involved here, there's going to be some energy wasted each time as thermal energy. Okay. The ball is going to warm up a little bit, the wall is going to warm up a little bit, and the energy is going to be transferred to the surroundings because it will be dissipated to the surroundings. Yes, I'm making you watch while I write it because it's such an important thing you must be able to say in this topic. I hope that helps. To answer this question, I have included both figure 15, the question, and figure 14 here because I'm going to link the two first. In trying to get my head around what this question is about, I've got to remember that this is part B of a bigger question, and so it links back to what the question started all about, this ball swinging from a crane to knock down a wall. After knocking down the wall, the ball will swing freely. So the ball is going to swing forwards and backwards and forwards and backwards, and it's going to keep doing that until it stops swinging. The graph is showing me how the height of the ball above the ground varies with the time during 3 of those swings. So we have got the ball starting up here. That is point A in figure 14. And then the ball swings down, and this is point B in figure 14. So the distance between there and there, this height above the ground, would be 1.5 metres. And this height here doesn't change, that's constant, because when the ball is stationary, it is hanging from a crane, which is a set distance from the ground. So that's why this bit here is a distance, we don't know what that distance is, but it's fixed. The ball can never get lower than that distance. So I've pictured a little bit more now what's happening in the graph by linking it back to the beginning of the question. Now let me think about what the graph itself is showing me. So I find it really useful when talking about a graph to number bits on the graph, so that when I'm writing my answer, I don't have to keep writing out things to explain which bit of the graph I'm talking about. So I am numbering each bit of the graph I want to talk about here, so that it's easy for me to refer to it. Okay, at 1 here, we have got the maximum gravitational potential energy that ball will ever have in this graph. The ball is going to go from GPE at 1 to kinetic energy at 2. And here, that is going to be the maximum kinetic energy the ball ever had. Okay, here the ball is swinging forwards, it's swinging down, and then it's staying swinging forwards because then it swings back up again. The gravitational potential energy comes from the kinetic energy. So the ball swings, it gets lower and lower and lower as it gets faster and faster and faster, and then it gets higher and higher and higher as it gets slower and slower and slower. So the gravitational potential energy is changing into kinetic energy. The kinetic energy is then changing back into gravitational potential energy. All the way through 1 to 3 is a forward swing. Now, point 3 here is lower than point 1 here. There is a difference in height. And that is because this is not 100% efficient. I'm definitely going to have that in my answer. There is not an efficient system here. And that is because of friction. There'll be friction, particularly air resistance, and those keywords will be in my answer. Friction and air resistance are causing some of the gravitational potential energy to become thermal energy, some of the kinetic energy to become thermal energy. And that's going to happen all the way through the swing. Because of friction and air resistance, there is going to be some of the energy transferred into thermal energy. The ball is going to warm up, the air is going to warm up, and the wall, that first hit, the wall is also going to have some energy transferred to it too as it moves and heats up. So when the ball is swinging, it's never ever going to be able to swing back to the height of 1.5 metres above its B position. It's always going to swing slightly less, a slightly smaller distance of each swing, because some energy is going to be wasted on each swing by being transferred into thermal energy. And that thermal energy is going to end up dissipated, very important keyword, and that's going to end up dissipated to the surroundings. So the wall, the ball, the air. The energy that's being dissipated is wasted energy. So not all of the gravitational potential energy becomes kinetic energy. Not all of the kinetic energy becomes gravitational potential energy, and so on. So we've had one swing forwards from 1 to 2 to 3. Then the ball will swing backwards. So it will swing back towards point B from figure 14. At point 4, that's where it will have kinetic energy again. 3, it had its gravitational potential. And then it will continue going backwards but climbing up the other side to end up back in almost its original position but lower down because of all the energy that's been wasted and dissipated to the surroundings. And then that is just going to continue. So the gravitational potential energy is going to become kinetic energy again. There'll be forwards there. And that will continue until there is no energy left because it's all been wasted. Because all of the energy over time has become dissipated to the surroundings as thermal energy. I hope thinking through that has helped. Let's see what the final answer looks like.